All right, get ready because today we are going to dive into particle physics.
Oh, exciting.
But you don't need a PhD to follow along, I promise.
Okay, good.
We're going to be talking about how scientists are using AI to find new particles.
Okay, cool.
And the secret weapon is something called symmetry.
It's super interesting, yeah.
So basically, we're going to be looking at this paper, and it's called Optimal Equivariant Architectures from the Symmetries of Matrix Element Likelihoods.
Catchy title.
Yeah, I know it's a mouthful,
Oh.
but the ideas are way cooler than the title makes them sound.
Oh, yeah, definitely.
So,
The researchers are really focused on this thing called the matrix element method, or they call it MEM.
okay.
And it's like,
Man.
yeah, like a toolkit for detectives, but for physicists.
Oh, a detective's toolkit.
Yeah, so like imagine a particle collision,
Okay.
like a crime scene.
Okay.
And you've got all these pieces scattered around, like the particles that are detected after the collision. And the MEM helps the physicists put the pieces together, figure out what happened and what kind of interaction created those particles.
So we're reconstructing the crime of the particle collision?
Exactly.
Oh, that's a good way to put it.
Yeah.
So where does AI fit in?
Well, that's where it gets really cool.
Okay.
So by building in the same symmetries that physicists use to understand the universe, we're basically giving AI a head start in understanding those rules.
Oh, okay.
It's like we're giving it a cheat sheet.
Ah, so it can learn more efficiently.
Yeah, exactly.
Okay, I see how symmetry is important here.
Mm-hmm.
But this paper talks about optimal symmetries.
Yeah.
And that's where my intuition kind of breaks down.
Well,
Why wouldn't you just use all the symmetries if they're so helpful?
right, you would think that, but it turns out that's not always the best way to go. It's kind of like trying to solve a simple math problem with calculus.
Oh, okay.
Like it's just overkill.
Yeah.
And the researchers found that if you feed the AI all the possible symmetries, it can actually slow it down.
So it's about finding the right symmetry for the job, like using the right spice in a dish.
Exactly. Like too much or too little can really throw things off.
Okay.
And one of the symmetries that was super important here was longitudinal boost invariance.
Okay, what is longitudinal boost invariance?
So it basically means that the laws of physics look the same whether you're standing still or moving at a constant speed in a straight line.
Okay.
So imagine you're watching a game of pool,
Okay.
like billiards.
Yeah.
It doesn't matter if you're standing by the table or if you're walking next to it. The physics of the balls colliding is going to be the same.
Okay, I get the concept, but how does that help AI find new particles?
So by building this type of symmetry into the AI, the researchers could really simplify the problem.
Okay.
It's like giving the AI a shortcut.
Oh, okay.
So it can focus on the important stuff without getting bogged down by the details.
So it's not just any symmetry, it's the optimal symmetry that unlocks the best analysis.
Yeah.
Okay, that's fascinating.
Mm-hmm.
Now, the paper also talks about this thing called the Dye-Higgs challenge.
Yes.
What's that all about?
So the Dye-Higgs challenge is kind of like trying to find a rare gem hidden in a giant pile of rocks.
Okay.
And the gem in this case is this process where two Higgs bosons are produced together and then they decay into these four bottom quarks.
Okay, wait, remind me what's a Higgs boson again?
Oh, so the Higgs boson.
It's what gives things mass, right?
Yeah, it's the one that gives other particles mass.
God particle, yeah.
Exactly, that's the one.
Okay, so why is this Dye-Higgs process so important?
Well, it's really important because it helps us understand the Higgs boson itself.
Okay.
And how it interacts with other particles.
So we're trying to figure out more secrets of the universe?
Yeah, exactly.
But why is it so hard to find?
It's so hard to find because it happens so rarely.
Oh, okay.
And there's just a ton of other particle interactions happening at the same time.
So is that where AI comes in?
Yeah, that's exactly it.
To sort through the data?
Yeah, to find that needle in the haystack.
And symmetry is the key.
Exactly. Understanding and using the right symmetries can make the search way more efficient.
So it's not just about finding the Higgs boson, it's about finding new types of particles we haven't even thought of yet.
Yeah, that's the really exciting part.
That's crazy.
Yeah, we're giving AI this whole new way of seeing the universe.
Okay, but before we get too carried away, let's go back to the Dye-Higgs challenge.
Okay.
How did they actually tackle it?
Right, let's unpack that.
Yeah.
And look at the steps they took to prepare the data and build these AI models.
Okay, sounds good.
Welcome back.
All right, so we've got our detectives toolkit, the matrix element method, and our secret weapon, optimal symmetries.
Right.
So how do we actually put those to work?
So they started by looking at the data itself.
Okay.
And remember, this is from the Large Hadron Collider.
Right.
It's really messy and complex.
Yeah.
like trying to find a whisper in a hurricane.
Oh, wow.
So they had to prepare the data so the AI was looking at the right stuff.
Okay, so what did they focus on?
They started by looking for the 4 most energetic bottom quark jets that were produced in each collision.
Okay, so those are like the smoking gun.
Exactly. Those are the ones most likely to be from a Higgs event.
Gotcha.
And then they used an algorithm to group those 4 jets into 2 pairs.
Okay.
Each pair would represent a potential Higgs boson decay.
So they're not just looking at individual particles,
Yeah.
they're looking at how they're grouped together.
Yeah, it's like analyzing the relationships between suspects at a crime scene.
Okay.
But they went even further.
Okay.
They looked at jets beyond those main 4.
Why? Wouldn't that just be more noise?
Well, think of it like this.
Okay.
At a crime scene, you might have evidence from people who weren't directly involved,
Okay.
but still offer some context.
Right, witnesses.
Exactly.
Gotcha.
So they included these extra jets,
Okay.
but they gave them lower weights so they wouldn't mess up the main evidence from those 4 bottom quark jets.
So it's kind of like additional info, but not as important.
Exactly.
Gotcha. So once they had the data all prepped and ready,
Right.
what kind of AI did they actually use?
Well, this is where things get really impressive.
Okay.
They developed a new neural network, but instead of getting into all the technical stuff,
Okay.
let's think about it conceptually.
Okay. Sounds good.
Imagine the network is like a game of telephone.
Okay.
Each node is like a particle,
Okay.
passing messages to each other,
Okay.
learning about the relationships.
So they're talking to each other.
Exactly. Sharing information.
Okay.
But the key is that this network is equivariant.
Equivariant.
Yeah. So it means that the network's output changes based on the input.
Okay.
It respects the laws of physics.
Okay, like that longitudinal boost invariant.
Exactly. It's built to account for that.
So it understands how physics should work,
Right.
not just crunching numbers.
Exactly. It's following the rules.
Okay, and that makes it more powerful.
Yeah. And they actually tested different architectures.
Okay.
Some more complex than others. Some incorporated the full Lorentz group.
Oh, wow, Einstein.
Yeah, all that space-time stuff.
That's pretty heavy.
Yeah. But it turns out they didn't really need all that.
Oh.
The ones that used just that longitudinal boost symmetry actually worked just as well.
So simpler was better?
Sometimes,
Yeah.
yeah.
Okay.
And it's really about finding that optimal level,
Right.
not just throwing everything at the problem.
So less is more.
Sometimes, yeah.
They also experimented with that permutation symmetry thing.
Yeah.
The order of the particles.
Right.
Remind me why order matters again.
So it depends on the interaction you're looking at.
Okay.
Sometimes the physics is symmetrical, so order doesn't matter.
Okay.
But other times the order can be really important to understand what happened.
Okay.
So they had to be careful with this one too.
Okay.
And what they found was that the best approach depended on if they were looking for a resonant or a non-resonant Higgs signal.
Wait, resonant versus non-resonant?
So resonant involves an intermediate, heavier particle that decays into the 2 Higgs bosons.
Okay.
So it's like a chain reaction.
A two-step process.
Right. Non-resonant is just a direct production of those 2 Higgs bosons.
One step.
Exactly.
Okay.
So for the resonant signal, they found that using a less strict permutation symmetry worked better.
Why would that be?
Well, with that intermediate particle involved, it gets more complicated.
Okay.
The order of the bottom quarks isn't as crucial because you've got this extra step influencing things.
Okay, so less strict, more flexible.
Exactly.
Okay.
But for non-resonant, where there's no intermediate particle, a stricter symmetry was better.
Because the order matters more in that case.
Exactly. It all goes back to understanding the physics and choosing the right approach.
Right tool for the job.
Exactly. And speaking of tailoring, they also made another interesting discovery about complexity.
Oh, this is the smaller's better part.
You got it. They found that those smaller networks with fewer parameters,
Okay.
those actually performed really well, especially when they didn't have a lot of data to learn from.
So like a small specialized team versus a giant bureaucracy.
Exactly. Finding the right balance is key.
This is so cool.
Yeah, it's really fascinating stuff.
Okay, so now for the moment of truth.
Right.
How well did they actually perform in this Higgs challenge?
Let's get into that because the results are pretty remarkable.
So we've got the detective work, the data wrangling, the AI algorithms.
Right. It's all come down to this.
Yeah, the results. How did they do with this Higgs challenge?
Well, the ones that had that longitudinal boost invariance.
Okay.
Remember that elegant principle of physics we talked about? Those were the clear winners.
Wow.
They beat the more complex models like by a lot.
So simpler was better.
Yeah. It really shows you that understanding the physics and picking the right symmetries is key.
And they also found that the best way to handle that permutation symmetry,
Right, the particle order.
yeah, that it depended on whether they were looking for a resonant or non-resonant signal.
Huh. Exactly. And it all comes back to understanding the underlying process.
Okay.
For resonant, where you have that intermediate decay, less strict permutation symmetry was better.
Because it's more complicated with that extra step.
Right, more flexibility for the AI.
Makes sense.
But for non-resonant, stricter symmetry was the way to go.
Because the order matters more when it's a simpler process.
Exactly.
It's all about the right tool for the job.
Couldn't have said it better myself.
Now, what about that model complexity thing?
Oh, right. So they found that those smaller networks, the ones with fewer parameters,
Yeah.
sometimes those actually did better.
Really?
Yeah, especially when they didn't have a ton of data.
So it's like David and Goliath, small and nimble can win the day.
I like that analogy. It really highlights the balance between complexity and the data you have.
This is really making me think differently about AI.
It's pretty amazing stuff.
So where do we go from here? What does this mean for particle physics and AI in the future?
Well, this shows us that these symmetry-informed techniques could really change how we look for new particles.
Yeah.
They're helping us go through tons of data so much faster and more accurately.
And not just finding particles we already know about, right?
Exactly. The potential is there to discover completely new particles.
That's wild.
Yeah, things we haven't even imagined yet.
We've given AI a treasure map.
And who knows what it'll find.
This really shows that the universe has so many hidden connections and patterns.
And we're just starting to figure them out.
It's pretty exciting to think about.
It really is. It's a testament to human curiosity.
And ingenuity.
By bringing physics and machine learning together, we're really opening up new possibilities.
It's an amazing time to be alive. Who knows what we'll discover next?